Hello. Hello.
Yes, sir.
Yeah, what's your name?
Ashweta Patnaik.
Okay. So I will start the today's discussion now with briefly going through the week 3 lectures. So I will be giving you a summary and then we'll go ahead with. So you didn't come in the last session, I guess.
Sorry?
You didn't come in the last session.
No, I haven't attended any last two session.
Okay. Okay. So the what we will doing is first summarize and then we'll do some questions that will be going to help you in solving the assignment problems.
Sure.
Okay. So so this week 3 lecture is mostly on the van der Waals interactions. The van der Waals interactions are ubiquitous in nature. These are one of the most important interactions that you will find anywhere. So it is one of the most important interactions that we find everywhere. So basically, VDW or the van der Waals interactions is divided into the three subcategories, or the three types of van der Waals interactions are present in the nature. That is Debye interactions, then we have Keesum interaction, and then we have London interaction. So the origin of Debye interactions is because of the permanent is because of the interaction between the permanent dipole and induced dipole. So permanent means inherent inherent to molecules because of some electronegative elements. So I will tell you in detail about this. And induced dipole are the dipole that you are inducing, or there is a induction. There is a dipole moment due to the induction. While in case of interaction, both there is an interaction between the two permanent dipoles. And permanent dipole. And in case of London interaction, it is induced dipole and induced dipole. The important thing about all these interactions is all are attractive in nature. So that is the one of the key thing about these interactions. So the complete van der Waals interactions is the sum of dipole interaction plus key sum interaction and the London interaction. So we need to understand what dipole is before going to understand what is permanent or the induced dipole. So dipole is a pair of electric charges of equal magnitude, but of opposite signs. Like dipole exists something like, so this is Q and this is minus Q and this is plus Q. And this is plus Q. So we have this and this together constitute a dipole. Let's say this distance is L, that is the L is the distance between the center of nuclear center of the charge. So this is the dipole. That is the dipole. The dipole moment, as sir introduced us in the lecture, is mu, that is the symbol being used for the dipole moment, is equals to Q into L. L is the distance between these two charges. So now, as we have discussed that uh, there is a different kind of interactions which leads to the different characterization like dipole interaction, key sum interactions on the London interaction. So we need to understand what is permanent dipole or the induced dipole. So the first we'll discuss about the permanent dipole. So the permanent dipole, basically like you are having a H2O molecule. So because O has higher electronegativity than hydrogen, so it has partial positive, so it constitutes a partial negative and partial positive charge, and so this are the dipoles. So that is inherently present in the H2 molecule. Inherently present in the H2 molecule. So when we have such kind of two different permanent dipoles, Then we have the VDW force, that is because of the Esom interaction. Now, what is induced dipole? So induced dipole is like you are having a atom with nucleus and some electrons. So it has it is electron neutral. But when you put some let's take let's say you take some one dipole near to this atom. Oh, sorry, near to this molecule. If this is a molecule, so I can say like uh, so this is a electron neutral molecule. It doesn't have, so initially it is electro neutral, but when you put some, so you have some dipole here like this. So due to this, so because this is near to the positive charge, so there is a induction, and due to this induction, there is a dipole induced in this molecule, and due to this, it becomes negative, and this is positive. So this is the example of induced dipole. And when we look at when we look at the interaction between these kind of species, that is induced dipole and permanent dipole, then it is called to be as Debye interaction. Okay. Any problem? Any question till now? So now the last one is the London dispersion or the London force or the London interaction. So in case of London interaction, we have this induced dipole. We have two induced dipoles. So there is an interaction between two induced dipoles. Now the question arises that why is it possible without any permanent dipole? There is a possibility of induced dipole. So there is a possibility. There is a possibility because if you have a if you have one molecule and it has one atom, and because of some disbalance, there is a electron cloud. Some electron cloud uh, come together, and due to which, and this is positive charge. So when we have some negative charge accumulated at one side due to some disbalance inside the uh, atom. So due to this, there is a, so in this case, it is delta negatives. It is one of the atom, and so due to this, the whole molecule is now have a induced dipole. So this kind of so we are having induced dipole, and now we are when we are looking at the two induced dipole interactions, then we called it as London interactions. So this is all about the fundamentals of the different kind of attractive interactions, attractive van der Waals interactions. So after that, there is a discussion on uh, on the forces that are calculated. So forces and the energy. So the energy between the, let's say, so sir has discussed induced dipole. So for the case of uh, or for the case of uh, ion dipole interaction, so in case of ion dipole interaction, we are having a ion, let's say some ion that is having a charge Z, and there is interaction between this with some dipole, and this distance is given as R12, and this is L by 2, this is L by 2. So the formula that comes out for the energy of the system or the interaction energy is Z E Q L by 4 pi epsilon naught 1 by R12 square. So this is for the case of ion dipole interaction. It is there, the derivation is there in lecture, but I'm just summarizing it. If you have any doubt in this, you can ask. Any doubt? Hello? Devanu?
No doubt, sir.
Okay. So what happened if we have a, instead of this, we this dipole is arranged at some angle. So that is already also discussed. So we have this kind of, and so this is, let's say Q, this is Q, this is R, this is R12. Let's say this is plus, this is minus. And this is some angle theta at which dipole is aligned. So the interaction energy comes out to be Z E Q L cos theta divided by 4 pi epsilon naught to 1 by R12 square, considering the fact that L by R12 is less than 1. So the physical significance of the assumption is just that the distance between the two uh, charges present in the dipole is very small than that of the distance between the interacting molecule or the ion. So now these are the with this way we can arrive at different kind of so you can derive this. So in the book by Israeli, so I can check the correct spelling. So all of these different kind of interactions are given in that book. I'm going to give you a name. So this is Jacob and so this is the book by Jacob. And Israel theory, that is intermolecular and so in this all of some of the derivation are also given with all these kind of interactions. So if you want to read more in detail, you can go through that book. Okay. So now after that, now we know we have different kind of interactions. So we have ion or ion, permanent dipole, or we have permanent dipole, permanent dipole. Then we have permanent dipole, induced dipole, then we have permanent or induced dipole. Induced dipole. So the main characteristic of these kind of interactions are so ion and ion permanent dipole. If you see the final uh, sign of the energy can be positive or negative, and the so ion goes as 1 by x or 1 by r, I can say, and this goes as 1 by r square. So r is the distance between the two ions, or r is the distance between the ion and the permanent dipole. So it may be negative or positive, which means it can be attractive or repulsive. But the main feature of these kind of interaction is that it always goes as minus 1 by x to the power 6. So as it has a negative sign, and so it is always attractive in nature. I can also show you that how this one-to-one interaction, I will quickly show that. I've already derived it. So So here I have taken it from the book that I just told you. So here we started by considering this charge and this dipole, and we find out the interaction energy between that. And so what we get is basically due to this dipole, we will be going to get the electric field on this charge, so which is acting in three directions. So we have a component of electric field on the charge, that ion, due to the dipole. So now we have calculated so we have this force. Now we have another dipole instead of that. So we have generalized it in a way that this charge is, now we are having a dipole here, and so it is affected by the electric field due to the another dipole. And so when we generalize that, so we got that the electric field due to this dipole here is is the is the summation, or is the magnitude of the parallel and the perpendicular electric field. So when we resolve these components and we find out the net field, so this net field is going to affect the dipole at the another dipole that we put. And so we have found out that it goes as r to the power 6. So this mu is the dipole moment, and we have calculated if we are having two molecules having a permanent dipole moment mu1 and mu2, then we can get we have this kind of interaction, that is dipole induced dipole. So any doubt? If you have any doubt, you can ask if there is issue in understanding this. Hello.
No doubt, sir. No doubt.
Okay. So
That was the W in polar form, right?
yeah,
That Van der Waals. Yeah.
it doesn't. So it's in 1D actually, so it doesn't. So then we have this. So my point, I wanted to show you that this is r to the power 6 and this is attractive in nature. You will go through this book and you will see that. So we have So finally, we have discussed Debye interaction, permanent this key sum interaction, and the London interaction. So the total interaction can be looked at out like this. So the final interaction is something like this, which looks like one by 4 pi epsilon naught square 2 alpha mu square plus 2 mu to the power 4 3 kbt plus 3h by 4 mu alpha square r to the power minus 6, and this corresponds to the net beta x to the power minus 6. Beta is in constant. So this is coming from the dipole, oh sorry, Debye interaction. This is coming from the sum interaction. And this is coming from the London dispersion. Okay. So we have this. On this, we will be going to solve a numerical afterwards. So then,
In the,
yeah,
I have a doubt. There is a 3 by 4 in the London,
yeah.
because it is given in the assignment 3 by 4, but in the video it is given only 3h. 3h alpha square divided by b.
One minute, I have to check it. I think it's 3 by 4 only, but I can
It
check
is
it.
given the, that's what it is, whatever it is written here, it is given in the assignment, but in the video it was not there. 4 was not there in the video, I don't know. So I have a confusion on that.
But I don't know. There's a 1 minute. Mm, I can check it in the kitchen. Mm. This kind of form is not. Look at this. In both the videos, it is not there. I think it's.
It is not there, and even in the problems also, there was no 3 by 4 was not there. Only 3 was there.
In the problems means like.
In the problem video also, which is
Okay,
there
okay.
in the,
Yeah.
yeah. And one more thing, have it out in the assignment 3. First question is given. There is no mention of temperature is also there, but we
When
require
so when
temperature.
yeah when the temperature is not given, then you can assume it as a
No,
room temperature and you can solve it. You will get the correct answer. So what I was thinking is for the case of keys, sorry,
London.
it's the London dispersion.
Yeah.
So in case of London, it's look like 2 shouldn't be there because 3/4 alpha square h nu by yeah 3/4 should be there.
3 by 4 should be there.
Actually, yeah, 2 should be there. So this is 3/4 h nu. Because according to the book, what I am looking is 3/4 should be there. Until I mean like there shouldn't be any mistake in the book. So Yeah, 3 by 4 should be there. And there is one more thing need to be rectified, and there may be a typo. I will ask you to. So that is 3H nu. 3H nu alpha square by 4. Yeah, correct.
It is 3H nu.
Yeah, 3H nu.
But means that will be corrected in the assignment also. 3H 4 nu. 3H divided by 4 nu alpha square is there in the assignment.
Yeah, their nu should come above, and
Nu to be in, okay.
and I think one separate formula written where it is for induced dipole and induced dipole. So where phi London is given as minus 3H by 2 mu1 plus mu2 divided by alpha naught 1 alpha naught 2 divided by 4 pi epsilon naught square 1 to the power r to the. So it is given in the lecture, I guess. So I think this should be according to book. So what I'm saying is according to book, but I don't know if I need to check it again, and we'll discuss with sir, and then we'll do something. Give some announcement. So this should be minus 3H by 2. The corrected form is this minus 3H by 2 mu1 divided by mu1 plus mu alpha naught 1 alpha naught 2 divided by 4 pi epsilon naught square 1 pi x to the power 6. So this is according to this book that Jacob is managing.
One
Right.
second, sir. There is a nu 1 plus nu 2 should be there, no? Divided by nu 1 into nu 2. How come it will be changed?
What
In
you
the
are saying?
second, I am telling that in the second equation, minus 3h divided by 2, nu 1 plus nu 2 divided by nu 1 into nu 2 should be there, no?
No, new one. What you are saying?
And nu 1 plus nu 2 divided by nu 1 into nu 2 should be there, no? In the from the above equation, it is.
Yeah, that's why you are saying that. So that's what I'm saying. No, this is the rectification, and that's why this H nu is above.
So the purple one is the right one.
This one is corrected one. This pink one.
Yes, yes, yes. Okay, okay. Sure. And if it is nu 1 and nu 2 are the same one, then it will be coming out to be minus 3h into
Yeah, 3/4.
minus 3 by 4h nu into nu should be in the numerator and alpha square by 4 by epsilon square 1 by x6.
Yeah.
Yeah. Okay. Got it.
Just 1 minute. But I will check this, sir, and let you know. So meanwhile, we'll go ahead. So I will be so I will be going to give one numerical on this. So try to solve it, and we'll then discuss the answer. So we have a phenol, and anisole, and we have these values mu to be 1.55, 1.25, alpha by 4 pi epsilon naught into 10 to the power 30 is 11.6, 13.7. Beta into 10 to the power 77 is 6.48 and 7.22. So calculate the percentage contribution of London dispersion, force of interaction, and Debye interaction in the total van der Waals interaction. So try to solve this and then we'll see. We'll check the answer. So you need to find out the phi divided by phi VDW into 100 and phi London divided by phi VDW into 100. Okay. So can you try this and like once you any of you get the answer, just let me know.
Sir, for once, can you revert back to the like equation? Hello.
I am waiting for the answer, so whenever you get it, just let me know. Devaru, are you solving it? Hello, Devaru.
Yes, yes, we are doing. So 5D was found to be 0.0824.
Did you get that?
Yes.
What's the answer?
Complete answer I didn't able to find out till now, but only I have found out that one Debye interactions for the phenol. It was found to be 0.08024.
0.08.
Up to that, okay? Okay, sure.
Okay. I don't think that's correct.
No, only for DB interaction for phenol, it was wrong.
Yeah. Did you put the value of Dubai?
Yeah, because in the first I calculate the mu was
Right.
found to be 1.5 into 3.33 multiplied by 10 raised to minus 30 coulomb meter. So it was found to be 4.995 into 10 raised to minus 30 coulomb meter. Then the value for the alpha by 4 pi epsilon naught is multiplied by 30 is 10 raised to 30 is given 11.6. So alpha by 4 pi epsilon naught value is found to be 11.6 into 10 raised to minus 30.
1 minute.
So, so can you then do it, please?
So we'll try this question. So as you know, phi d is phi d is 2 alpha dipole moment square divided by 4 pi epsilon naught square, correct? So we know the value of mu. We know alpha by 4 pi epsilon naught. So what? So 2 into alpha by 4 pi epsilon naught into mu we know divided by 4 pi epsilon naught. So we have 2 into, so for this 11.6 into 10 to the minus 30 into mu square. So mu is the dipole moment and that is 1.55. Correct.
1.5 only, no? Oh, okay, 1.55.
1.55 whole square. Yeah.
Oh, no.
Yeah.
Yeah.
And that has to be multiplied with d by
3.33.
3.6. Yes.
sorry, into 10 to the minus 30.
Square.
Yeah, correct. And then 4 into 3.14 into 8.85 into 10 to the minus 12. So what? This is this the way you tried?
Yeah.
Okay, then
Divided by beta will be there, no? Divided by beta value, that is 6.48 into 10 raised to minus 77, no?
no, where the beta is?
This one, no? Beta into 10 raised to.
This, yeah, that is for the calculation of percentage.
Okay, okay.
Yeah, you can do that now also. So 5 percentage is this divided by beta. So that should be divided by,
Sir, can you go back to the main equation once?
okay,
Just once.
yeah.
I got a bit confused. Okay, thank you, sir.
So feeding is this divided by beta. So beta is 6.48. Right, all right. That is
6.48 into 10 raised to minus 77.
and this becomes
This becomes
into
0.08.
that should be in percentage. So what you are getting?
No, after without multiplying 100, the answer was coming 0.080.
Yeah, that is around 8.6%, I guess.
How
Check.
come it will be 100 means 80.2. So it will be my answer is coming 8.0.
Yeah, it's 8.58. 8.6%. You may check that calculation again.
Yeah, I have substituted 1.5 instead of 1.55. So maybe that.
Yeah, and so we need to calculate what is. So can you now try? We need to calculate the van der Waal. So, but we don't have this new values for this. So we can use this key sum and assuming at a room temperature to calculate this key sum, and then we subtract these two values from this and we'll get the percentage of London dispersion. That is, I can write
1 minus Kisam, 1 minus Kisam minus Dive. Then we will get the London.
yeah. That is into 4, 5, 7, not in. Can you try it?
Yeah, I'm doing.
Any answer?
Nine 9.31.
What?
The answer was 9.31 into 10 raised to minus 77 was the Kesam force.
Okay.
Then it should be divided by beta multiplied by 100. It will be 9.93.
Can you calculate it completely?
Yeah. Fourteen point three. Is it correct? Minus 7.
Yeah, so I have checked with sir also. So that's about the expression. So this is the correct expression only, that what I just now told. So this is the correct expression. Okay.
Okay.
So then, yeah, what you are saying is, are you able to get in the percentage? The
That
final
was 14% for the key sum.
for the
14,
some 14, yeah, it's around 14.5%.
14.3 is actually the same.
Yeah, something like that. And then you can, from that, you can calculate what is London. So 100 minus 14.5 minus 8.6, and that comes out to be 76.9. Okay.
The previous one you told, no, it is a 86% or 8.6.
No, it's 8.6%.
Okay, okay.
Yeah. So that is for the case of
London.
this is for the case of phenol.
Yeah.
All these. So you can try, and I am giving you an answer for the case of anisole. So uh, it is coming out to be 6% for for Dubai, and for London it is coming out to be 88.5%. So you can go back and check it.
Okay.
Okay. So now with all this discussion, sir has also discussed about the. So we'll go through the discussion of a van der Waals interaction with particles. So before going to this discussion, I will just also have one more numerical that is of relevance to you. So find out the so if the potential energy of two molecules is given as U is equals to A by R to the power 12 minus B by R to the power 6, then find out the equilibrium position and the energy at this position, given that A is equals to 32B. So this is given. Sorry, 64. And yeah, 32B. Okay. So options are okay, you can calculate the equilibrium position and the energy of this. You need to calculate. Do you know how to calculate it? or give a try. We'll then discuss it. So I'm giving an option for equilibrium position. Options are 4, 2, 8, 1. And for energy, options are
Sir, I guess here we have to can you hear me?
yeah, I'm hearing you.
We have to since A is given as 32B, so by converting all the terms in B and R, so we need to differentiate minus du dr since potential energy is
Yeah,
given.
yeah, correct.
So,
To find out the equilibrium, yeah, you have to differentiate it and you have to
yeah, we have to
minimize,
like A and B, there are
minimize.
two constants, but we have to maintain uniformity. We have to convert it and then differentiate minus du dr by keeping the constant and then differentiating r to the power 12 and r to the power 6.
Yeah.
এটা তো constant বটে। এটা খাতা পেন না। Sir, is energy option C? Sorry, option B. Hello.
Yeah, hello.
Is energy option B?
I don't think so.
Okay, might be my calculation mistake. Sorry. Sir, equilibrium position 2, energy equals to minus V by 128.
Yeah, correct. So what we do is we have to minimize this energy, so that is minus
Sir,
T.
sir,
Uh,
ain't equilibrium position 2?
sorry, is equals to 0. So what we get is R to the power 6 equals to 2B by 2A by B. And so when we substitute this, we get is 2 into 32B divided by this is to the power 4 to the power 1 by 6. So we get 2. And energy, so we need to find out energy when R is 2A by B. Correct? How did you solve it? Hello? Debaru, how did you solve it? Substitute the value of R. It comes to be A, R minus B divided by B to the power 6. Hello? Devaru? Hello, Devaru?
Yes, sir.
How did you get this energy?
Sir, by substituting the equation,
Which equation? Value of
sir,
R.
energy equals to minus du dr. Energy equals to minus du dr. Right, sir?
Yeah, yeah.
Hello. Hello.
Hello. No,
Can you hear me?
energy is
Now,
equals
now,
no, no.
now, if we can differentiate, okay, like
Yeah,
if we differentiate, because minus of that potential derivative is equal to energy, so that we, if we differentiate, that we are getting, keeping the constants as a and b, 12a by r to the power 13 minus 6b by r to the power 7, right, sir? Hello.
yeah. But I think
And from that we are getting r. Now in the expression of u, if we keep that value which we are getting, that is r to the power 6 equals to 2 into 32b by b. If we substitute that value, we can get that answer, minus b by 128.
so. So while putting this to be 0,
Yeah.
2A by B, R to the power 6 is equals to 2A by B.
Yes.
Now we need to find out the energy.
Yeah.
So
So a value is given in terms of b, so bb will cancel, 1b will remain, the square and single b term will cancel out, so minus b by 128.
A becomes 32B,
Yes, sir.
32.
B.
B comes out
r to the power 12, which is 2 to the power 12. So you can write as 2 to the power 6 into 6, then it will be easier to cancel. And yeah, I'm
So this
taking
will
comma.
become to the
Yeah, that is 2 to the power 5, and this is 1 by 2 to the power 7.
yeah.
Yeah,
So that comes out to be
b by 2 to the power 6, take 2 to the power 6 common. Sir, take 2 to the power 6 common.
yeah.
Minus 6, sir, that will be minus 6. Upar. Yeah. Now it is 1 by 2 minus 1, which is half.
Okay.
Sir, 1 by 2 minus 1, which is half. Another 2 will be there in the denominator, because we are taking 1 by 2 to the power
Yeah,
6
correct,
common.
correct, correct. Yeah. So that is 128. So this is
Yes.
okay. So this is then last thing that I wanted to discuss is just briefly go through the interactions between the particles and the wall. Interactions that we have discussed between the colloidal particles.
Sir, also I had one problem I forgot to tell you.
Yeah, tell me.
Sir, actually I joined the class a bit late, right?
Okay. Okay.
So my mail was not like authorized to the like notifications,
Okay.
but I got the assignments of hydrogen and etc. But the assignment number 1 and 2 of colloids didn't come to my like mail. Okay,
Okay.
and when the solutions came out, I checked out. I have missed on those two, and there was no like another alternative to resubmit the assignment, right?
Yeah.
So what can I do if you can tell?
I
I
don't
didn't.
know much about it. I think NPTEL team is directly handling it. It's not up to us.
Okay, okay. So I'll contact NPTEL, right?
Yeah, yeah.
Okay, okay. Thank you.
Can I answer this question?
Yeah. Did you tried any different way?
No, not this one. That what he has a query about the assignment.
Okay, okay, okay. You can answer. Yeah.
No, it's means he once he missed the two assignment out, then that six assignment to be given, then best six will be calculated.
Can you please repeat?
No, there is a 8 assignment we have to submit. You missed two assignment.
I
Even though
missed
you
2 assignments. Yeah,
yes, even though you given the two that two assignment also, they will only select the best six. So
best
you have
6.
time to best. You can give the assignment best six.
Oh,
Then
acha,
rest
there will
six
be
if you
like
get
for each subject there will be 8 assignments, right?
no for 8 week course there will be 8 assignment. Out of that they will take best six.
Okay, okay, okay. I got that. Acha, acha. Okay. Now, like for confirmation, the like time for us submitting the third assignment is, if I'm not wrong, is 16th August, right?
Yeah, it is so every Wednesday.
Every Wednesday. Okay, okay, okay. Thank you, thank you, thank you so much. Thank you, sir.
Okay. So what I was thinking is the another topic that I have to keep revise is that Hammaker constant and something related to that. So I think we'll discuss that in the next session. For today, it's too much, I guess,
Okay, sir.
because
Thank you,
it's a
sir.
separate big topic. So I will quickly go through that in the next session.
Okay, sir.
Is it all right?
Okay, sir.
So we can end the session now if you wanted. If you don't have any questions, so you can leave the meeting. If
Okay,
you
sir.
have, you can tell.
Can you discuss about that LJ potential?
LG potential.
Yeah.
So you are saying, so what you want to me to discuss on that? Hello.
Problem based on that actually. Any problem based on it?
Yeah, this is the problem on LG potential only. This one. This is LG potential only. Hello.
Okay, okay, I understood.
Yeah.
That.
Anything else?
No.
Okay then. Fine. You will leave then. You don't have any plan.
Okay. So I will leave the class.
Okay. Thank you.